Welcome to the ultimate mastery session on Class 10 Light. Look, if you've ever stared at a textbook and felt like reflection and refraction were just a massive, confusing jumble of lines, signs, and formulas, you are in exactly the right place. Today, we are transforming this entire chapter into a highly visual, easy-to-understand cheat sheet. By the end of this explainer, you're going to have the exact tools you need to absolutely crush these concepts on your exams. So, let's dive right in.
Here is our target for today's class. We'll be hitting 1. The magic of light. 2. Mastering spherical mirrors. 3. Image formation cheat codes. 4. Mirror formula and signs. 5. The bending of light. And finally 6. A final exam power recap. Section 1. The magic of light. Okay, before we even think about drawing a single diagram, we need to challenge how we observe the world around us. Imagine this. You're sitting at the kitchen table, you pick up a shiny new spoon, and you look directly into the inside of it. Suddenly, your face is completely upside down. But why does this happen? Well, that simple, everyday kitchen spoon is actually a working spherical mirror. It is perfectly demonstrating the physics of light right there in the palm of your hand. Now, before things get curved, we absolutely have to know the ground rules. Whenever light bounces off a surface, it follows two unbreakable laws of reflection. First, the angle of incidence is always equal to the angle of reflection. Basically, if a light ray hits a mirror at a 45-degree angle, boom, it's bouncing off at exactly 45 degrees. Second, the incident ray coming in, that imaginary perpendicular normal line, and the reflected ray bouncing off, they all sit perfectly flat in the exact same plane. And the coolest part here, these laws apply to literally any surface, whether it's perfectly flat or curved like a bowl.
Section 2. Mastering spherical mirrors.
All right, it is time to learn the language of the curve. There are two main types of spherical mirrors you've got to know. First up is the concave mirror. The ultimate memory trick here is simple. It's curved inward, right? Like you're walking into a cave. It reflects from that inside surface, exactly like the inside of our spoon. On the flip side is the convex mirror. This one is bulging outward and reflects light from the outside surface, kind of like looking at the back of the spoon. So cave means inward, convex means outward. Super simple, right?
Now for the anatomy. These are your absolute, non-negotiable terms before drawing ray diagrams. The exact center right on the mirror itself, that's the pole. Now imagine the mirror is just a tiny slice of a giant glass sphere. The center of that imaginary sphere is called the center of curvature. The straight line running straight through the pole and the center is your principal axis. And the magic sweet spot exactly halfway between them, that is the focus. It's the exact point where parallel light rays converge. So the absolutely crucial takeaway here is this exam lifesaver, R equals 2F. The radius of curvature, which is the distance from the pole to the center, is always exactly double the focal length. If your exam paper tells you the radius is 30 centimeters, boom, you instantly know the focal length is 15 centimeters. It is a guaranteed 1-mark numerical shortcut. Do not forget it. Section 3. Image formation cheat codes. Get ready to equip the weapons you need to conquer any complex ray diagram your board exams throw at you. Listen, you only need 2 lines to find an image, but I'm going to give you 3 powerful weapons to choose from. Weapon 1, any ray coming in parallel to the principal axis will always reflect directly through the focus. Weapon 2 is just the exact reverse. A ray passing through the focus will reflect perfectly parallel. And weapon 3, any ray traveling straight through the center of curvature will bounce straight back along the exact same path. It's just an easy 1-2-3 combo move. Let's see how those weapons apply. Take a mental screenshot of this 6-case table for concave mirrors right now. As you bring an object closer to the mirror from infinity, the image generally moves further away and gets bigger. But most importantly, the first 5 cases produce images that are real and inverted. That means they are actually formed by real light rays meeting up, and they'll appear completely upside down. But here is the really interesting part. Case number 6 is what I call the VIP case, and examiners absolutely love testing this specific trick. When you move the object extremely close, literally right between the pole and the focus, the rules just completely flip. The image suddenly forms behind the mirror. It becomes virtual, meaning it's formed by fake intersecting lines. It becomes erect, which means upright. And it's enlarged. Always, always be on the lookout for the VIP case. Now let's connect all this geometry back to real life. Why do we even care? Well, dentists use concave mirrors specifically because of that VIP case. They need an enlarged, upright image to see your teeth clearly. Concave mirrors are also used in torches to focus light into a massive, powerful beam.
Convex mirrors, on the other hand, always make things smaller and upright no matter what. That is why they are strictly used for car rear view mirrors. They take a huge, wide area of the road behind you and shrink it down so the driver can see absolutely everything safely.
Section 4. Mirror formula and signs.
Okay, this is the part where most students start to panic, but we are going to navigate this math safely together. Treat the mirror's pole just like the origin, that 0, 0 point on an XY graph from math class. Left of the mirror is negative, right of the mirror is positive. Above the principal axis is positive height, below is negative height. Now, here is a rule you need to etch in stone. The object is always, always placed in front of the mirror on the left. Because of that, your object distance, which we write as u, is always negative. Lock that in your brain right now.
Enter the final boss, the mirror formula. 1 over v plus 1 over u equals 1 over f. V is your image distance, u is your object distance, and f is your focal length. This formula right here is the ultimate master key for unlocking all numerical problems. Just plug your values in with the correct positive or negative signs, do the basic fraction math, and the right answer literally falls right out.
But the math doesn't just stop at distance. We need to know size too. Magnification, or M, tells us if the image is shrunk down or zoomed in. The formula is the height of the image over the height of the object, which mathematically also equals negative v over u. Now, here's a massive shortcut for you. If your final M is positive, the image is virtual and erect. If your M is negative, the image is real and inverted. It's basically an instant lie detector test for your ray diagrams.
Section 5. The bending of light. Okay, let's step completely away from mirrors for a second. I want you to picture this. You drop a perfectly straight pencil into a glass of water, and suddenly it looks broken or jagged right at the waterline. Has the pencil snapped? No way! You are witnessing refraction. This happens because light actually changes its speed when it travels from the air into the water.
Think of light traveling kind of like running on a beach. When you run from the hard sand, which is the lighter or rarer medium, straight into the ocean water, the heavier, denser medium, what happens? Your legs slow down, and you naturally lean forward. Light does the exact same thing. When it goes from a rarer to a denser medium, it slows down and bends towards the normal line. But when it escapes from that denser water back out to the rarer air, it speeds up and bends away from the normal. Let's look at how this plays out in the famous rectangular glass slab experiment. First, light enters the glass from the air. It hits the denser medium, so it slows down and bends towards the normal. Second, it exits the glass back out into the air. It hits the rarer medium, so it speeds up and bends away. Now, because the top and bottom sides of the slab are perfectly parallel, the bending in exactly cancels out the bending out. So the final emergent ray shoots out perfectly parallel to its original path. It has literally just been physically shifted over to the side.
Section 6. Final exam power recap. Wow, we have covered some absolutely huge ground today. Let's rapid-fire summarize all this to lock it permanently into your long-term memory. Concave means curving inward like a cave. Convex bulges outward. The radius is always double the focal length. Use your 3-ray weapons, parallel to focus, focus to parallel, and center bounces straight back. In your sign convention, remember that object distance u is eternally negative. And finally, refraction is really just light bending because it gets sluggish or speeds up when changing mediums. You now have the exact blueprint to ace every one of these questions.
You know, the absolute best way to study physics isn't just staring at a textbook, it's genuinely observing the world around you. So, here is my final thought for you to take away today. Next time you look into a mirror, or grab a kitchen spoon, or just stare into a glass of water, don't just mindlessly look at it. Ask yourself, is what I'm seeing right now real, or is it just a virtual illusion created by bending light? Keep questioning things, keep learning, and go absolutely crush those exams. Until next time.